Good morning, everyone, and welcome back to our AI weekly seminars. We have the upcoming schedule on the screen. Please, thank you for attending this session, and please join us in the subsequent talks today. We are privileged to have Professor Yu-Xiang Wang from UCSD, where he's an assistant professor of computer science. Yu-Xiang received his PhD in statistics and machine learning from Carnegie Mellon, and his research has been recognized by several research awards, including an NSF Career Award, Amazon Research Award, Google Research Scholar Award, and Adobe Data Science Research Award. And today he'll talk about deep learning and nonparametric regression. And we are glad to have him on this exciting talk. If you have any questions during the talk, you can use either Q&A or chat boxes to ask your questions, and I'll read your questions to Yu-Xiang. That being said, I'll leave the stage to Yu-Xiang.
Thank you, Mohammed, for the introduction and for inviting me to speak at USC. I'm glad to be here. And thanks everybody for coming to my talk. So today I'm gonna tell you a bit about our recent exploration in the area of theory for deep learning. So for those who know me and know my work, this is really the first paper that we worked on related to the theory of deep learning. So previously I focused almost exclusively on statistical machine learning and differential privacy topics. So we are also new and learning on the way. So if there are anything that you can point us to about materials that you hear about in this talk, yeah, feel free to reach out and ask questions and give comments, and those will be very we'll really appreciate your lending our expertise to help us with this line of research. All right, so the work is primarily done, and all credit goes to my student Kai-Xi Zhang. So the talk is about how deep learning works in a classical setting called nonparametric regression. And we're going to give a theoretical analysis and hopefully shed a light on this problem that hasn't been considered in the aspects that hasn't been considered before through traditional approaches. Okay, so here's what I'm going to do. I'm going to first motivate the problem by talking about the nonparametric regression and talking about some mysteries of the deep neural networks in recent years. And then I'm going to give a warm-up analysis about the two-layer neural network on the weight decay and how they perform on these nonparametric regression tasks. Before I talk about our main results with a deeper L-layer neural network and how it is a little bit surprisingly equivalent to some sparse linear regression with the with certain representation learning. Right, and if time permits, so I'll also give some ideas of how the underlying arguments work for us to get this result to work out rigorously. Okay, so machine learning and artificial intelligence has really revolutionized every aspect of our daily life nowadays, and it touched upon like so many different applications. At the very heart of many of these progress lies a single family of model called deep neural network. So this is now a much broader family. What I'm showing is a most classical and a standard so-called feed-forward neural network that basically takes the input and passes through a linear transformation and some nonlinearity. And then another layer of linear transformation and nonlinearity, and then stack all these recursive computation together until the very end, which ends up learning features that are more easily classified into different classes according to the supervised signal. Right, so that's the standard feed-forward neural network. interestingly, from the statistical point of view, the deep neural network is not very well understood at all. What typically happens is that people want to fit significantly more parameters than one has data to fit them, and the number of parameters is often on the same order as the size of the data set, or even larger. And from the classical view of statistical learning, so we want to somehow choose the right number of parameters for your parametric model so that you can balance the bias and variance, but it doesn't, the kind of classical wisdom doesn't seem to apply in the regime of deep neural network when we overparameterize, right? So I'm showing this figure from Misha Belkin, discovery of this double descent phenomena, which provides one possibility of how we can understand this. So it appears that the more overparameterized the neural network model is, the easier it is to generalize. And even though we are fitting the data perfectly, so notice that the training risk or training error is already at 0, we are not actually overfitting. And the more overparameterized it is, and the less the model is overfitting, right? So why that is happening is still a bit unclear, like in the fully general setting with a deeper neural network. Another thing that remains a mystery is that optimization seems to be easy, despite the fact that the training objective function for fitting the deep neural network is a highly non-convex optimization problem. Yet with learning algorithms like stochastic gradient descent, like in almost all instances, like we don't really see any challenges for SGD to find a satisfactory solution that does well in practice. Arguably a more interesting question to ask is why do neural networks work better comparing to classical methods? So there had been a lot of work to try to explain the power of neural networks through different angles. So some may argue that neural networks are universal functional approximators, but so are kernels and splines, right? These classical tools are also universal functional approximators. Why do neural networks do better than these? And some may argue that neural network offers flexible representation learning, and it is a modeling language that one can maybe encode the domain knowledge through the architecture of the neuron, different layers, and to try to encode certain information, to encode the inductive biases that make the problem easier. But so are other traditional approaches like probabilistic graphical models and probabilistic programs and so on. In addition to that, one could the overparameterization, as one have like this is a very popular research topic in recent years on the theory of deep learning, has been studied through the angle of traditional tools like kernel methods. So neural tangent kernel is one particular family of approaches that studied the overparameterization in neural network. Yet the explanation is not specific to neural network, and some of these so-called benign overfitting phenomena in the interpolation regime also happens in linear models, right? So all of this seems to suggest that maybe like we need something more and something new to understand why do neural networks work better than the traditional approaches. So the gist of the high-level idea of our approach to this problem is the so-called adaptivity conjecture. So we believe that neural networks are not necessarily stronger than classical method in any specific problem. So take the problem of curve fitting, right? So given noisy observations of the data can be come up with a curve that nicely estimate the underlying ground truth, right? So in such problems, we already know that there are a lot of classical methods that has been shown to be min-max optimal, and one really cannot do better than them in the information theoretic sense with any other algorithms, right? But the standard practice, so maybe how neural network work better is not because it is able to do better in these classical problems, but rather it is easier to work with using these standard practices. In particular, maybe one can one can do as well as any of the classical method is able to do on each specific problem by tuning a standard set of hyperparameters like learning rate and weight decay, right? So maybe just doing this would allow us to choose the right level of abstraction and to avoid the need of carefully specifying the problems and checking the conditions, because it automatically adapts to the right set of assumptions that are needed to solve each specific problem. Right, so that's a high level. Yeah, so there's a question in Q&A, like what does the better mean? What makes you think that neural network will do better than kernel-based method? It'll be clear that just in a few slides. Okay. So the specific problem that we are considering in attacking this hypothesis of
quick question.
Non-parametric regression. Yes.
So what does better mean? What makes you think that neural networks do better than kernel-based methods?
Yeah, so I'll explain this just in the next slide.
Okay.
Okay. So yeah, it'll be very clear. So we consider this problem of non-parametric regression where the observed data is just the input-output pairs. So we have a fixed design, it's x1 to xn, and the labels is noisy, but there's some underlying function that comes from a certain function class, right? So this is like under relatively weak assumption when we assume these functions in this function class are differentiable or twice differentiable, and so on and so forth. So this is a very classical problem that has more than half a century of associated literature, and there are many approaches to this, and many of these approaches have been shown to be optimal for specific function classes. Okay, and depending on which community that you're coming from, you might know the problem of non-parametric regression as signal processing, signal denoising, filtering, smoothing, and so on and so forth. But they are all like they usually refer to the same set of problems with slightly different assumptions. The specific kind of non-parametric regression problem that we consider is a so-called locally adaptive non-parametric regression. So these are problems where the underlying functions had a heterogeneous level of smoothness across a different region. So specifically, some parts of this function has this high frequency. So on the left, we can see a Doppler-like function, and it has a higher frequency and less smoothness on the left, but it is much smoother. It changes much more slowly on the right-hand side. So in the middle, I'm showing a piecewise linear function, which has a similar property. So within this linear chunk, it is very smooth. It is as smooth as it gets because it's linear. But at the knots, when two linear pieces are joining together, and there's a discontinuity on the derivative, which makes it slightly non-smooth. And on the right, I'm showing a natural image which illustrates that in the two-dimensional image space, this is also the right kind of functions that we should look at, because the background sky and the jacket in the foreground or the grass, so they are relatively like low frequency signal, and they're much smoother, but they are sharp edges, and they are high frequency things that happening here and there as well. Okay, so the locally adaptive non-parametric regression problems, so they are also very classical, but there is an interesting. It requires a specific set of methods that tailor build for these methods for these problems in order to achieve the optimal rate. So let me tell you more about it. So the point is that like all the neuron tangent kernels and other kernel methods, like all the kernel-rich regression with an arbitrary reproducing kernel Hilbert space, they are strictly suboptimal for the locally adaptive non-parametric regression problem. So how do we state this formally, and how do we measure what we mean by better? So we need to define like this family of function classes. So let's consider the standard so-called total variation class, where the mth order derivatives of this function has a total variation that's bounded by some parameter c, right? So m is a parameter and c is another parameter. So this basically means that for m plus first order differentiable function, the absolute value of this function, say from 0 to 1, is smaller than C, right? So this is what it means. So the total amount of variation on the mth order derivative is smaller than C. So this is one prototypical function class that captures the idea of heterogeneous smoothness. And because this is L1, right, so you can put the variation here or put the variation there. So as long as the total amount of variation is small, then that is fine. It is known from Donahoe and Johnston and Memmel and Vandergeer and so on that the minimax rate of solving this problem in estimating the underlying function goes to 0 as the number of data point gets bigger with this rate, right? So this is an optimal rate that applies to any method. There's a lower bound and there are upper bounds that matches this lower bound. But the best achievable rate for a class called the linear smoothers, so which includes the neuron tangent kernel, goes to 0 at a much slower rate, right? So if we look at it, take M to be 1, so this is a family of piecewise linear functions. So we are looking at n to the power of -4 or 5, and for this one, we're looking at n to the power of -3 or 4. So for large n, the difference can be orders of magnitude. Okay, and this rate is a mean square error rate. So it's in the square scale. So that's why you can do better than 1 over square root of 10. Okay, so I hope that's clear. So the key question that we are asking is are deep neural networks locally adaptive, right? So we say some methods is locally adaptive if one can achieve the optimal error rate for these function classes. If we cannot, if we can do only as well as these linear smoothers, then we say that they are not locally adaptive. So the question that we're asking is, are deep neural networks locally adaptive? So if they are, then we know that it is doing better than kernels, and the neuron tangent kernels, they are not really explaining the behaviors of deep neural networks correctly. On the other hand, if deep neural networks are not locally adaptive, so maybe the NTK is indeed the right description of its theoretical property, but that also says that maybe we should like do better and come up with, and there are potential of coming up with way better methods than neural network on some of these problems. Okay, so we also wanted to study like what can neural networks do even better than classical methods that achieves a locally adaptive rate. So one particular type of problem is this like mixture of different type of functions. So on the left, I can have Doppler-like functions, but then the level of smoothness becomes m is equal to 1, or then it becomes like the piecewise cubic function and piecewise constant function, piecewise linear function. When everything is mixed together without us knowing where the right level of smoothness is, the appropriate level of smoothness should be used to describe each chunk of this function. The hope is that so maybe deep neural network is capable of handling the different chunks of these functions and estimate them appropriately by allocating the statistical power correctly to each chunk, right? So which arguably makes them even more locally adaptive than the classical methods. Okay, so I hope the question is clear. It turned out that as we started to work on this problem, we're not the first group of people who studied this. So answers partial solutions has already been worked out by groups of authors a few years before us. So in particular, Taiji Suzuki showed that the ReLU neural network that are carefully designed with a specific weight, depth, and sparsity constraint can be used to obtain the optimal rate for a broader family called Besov class functions, which includes the total variation class. But it requires a sparsity constraint, which makes it a bit hard to optimize. And these groups of authors, they consider the convolutional ResNet and again with a very specific design that get rid of the sparsity requirement. Yet the number of parameters in this network needs to be carefully tuned to say different M and different C, which specifies a particular choice of the total variation class. Haki and Nowak showed that the optimal rate can even be achieved with just a 2-layer neural network. right? Because they essentially established a representer theorem that says that the two-layer neural network that is sufficiently overparameterized is equivalent to a classical method called the locally adaptive regression splines. Yeah, so we'll look more into this just in a little bit, but before that, so let me state our punchline. So the main result from our work is that we showed that a parallel version of the so-called deep ReLU neural network achieves a nearly optimal adaptive rate, and they achieve that simultaneously for many function classes. And it requires us to tune only the weight decay parameter. Like, we don't need to do any architecture search. So the parameters of the width and depth of the neural network can be set to be like a fixed value, as long as it is sufficiently overparameterized, things are fine. As long as it is sufficiently deep, things are fine. And then we can achieve a nearly optimal rate simultaneously for many function classes. Okay, so as a disclaimer, so the statement applies to the arc mean of a certain objective function. So this is not a statement about the practical algorithm that trains the deep network using, say, the gradient-based methods. But we'll show some experiments to illustrate that our result actually provides some interesting guidelines for the practical experiments as well. Okay. So let me quickly tell you about the two-layer neural network, so which will set the stage and explain some of the tools that we can use to derive the more general result. Okay, so as a quick background, because I understand that not everybody here are familiar with a specific language in neural network, and maybe many people are not familiar with splines and piecewise polynomials and so on. So let's just bear with me if these are too rudimentary for you. So I'll do it very quickly. So we consider only ReLU activation functions, which is just rectifiers that truncate everything to 0 on the left-hand side. When things are smaller than 0, and when we refer to weight decay, and effectively we mean the square L2 regularization on the parameters. Okay, so the reason why it's called weight decay is because if we use gradient-based training, the gradient updates can be written as something that keeps shrinking the parameter by a little bit in every iteration. So that's the reason why it is called weight decay. But we're not dealing with the algorithm. We're dealing with the L2 regularized and L2 constrained version of the objective functions in this paper. So calling it weight decay, it should really be understood as the standard L2 regularization. Now, splines and piecewise polynomials. So it turns out these are like pretty critical and useful mathematical concepts for understanding neural network. So the splines are just piecewise polynomials where it's continuous and satisfies some additional smoothness parameters at the knots. And when we talk about knots, so these are the joins of the different piecewise polynomials together. And statisticians use splines to come up with methods for nonparametric regression, aka curve fitting. And the key of these approaches is they differ in how they choose where the knots are and how they fit these noisy observations. So for instance, like once the order of the spline is specified, say linear splines are just piecewise linear functions, and cubic splines are piecewise cubic functions, and it remains to choose the knots and then end up fitting the underlying functions for the chunks between each knots. Okay, so different methods do it differently. A method called smoothing splines. So cubic smoothing spline is arguably the most popular method for nonparametric regression in statistics. You basically choose all n of these observed data points to be a possible knots, to be the knots, and then you apply the square L2 penalty on the coefficients of a certain basis function. The so-called locally adaptive regression splines also choose all n input data points as possible locations of the knots. But then it is using the L1 regularization to select a sparse number of active knots, right? So in this way, this is the underlying reason why it can behave in the locally adaptive fashion. So splines are spanned by this basis function, which contains just a monomial basis, and the set of basis functions, once the knots are selected, called a truncated power basis. So for linear splines, so these are just a bunch of ReLUs, but shifted towards the location of the knot. And on the right-hand side, I'm showing the similar cubic spline basis when the M is taken to be 3. So these are the basis functions that can be used to span, right? Linear combinations of these span the entire family of splines of M's order. Okay, so enough of the classical background. So one of the key observations that this Pachian-Nowak work has made is that 2-layer neural networks are really splines. They are not approximating something called free knot splines, but they are representing the entire family of splines with a fixed number of knots. So in this case, there are M knots. So here's the only difference from smoothing splines and locally adaptive regression splines is that the neural networks, they're not fixing the knots ahead of time, but rather specifying the total number of knots while optimizing over where the knots are, right? So how are they equivalent? So let's take a closer look. So basically, what you can do is to just divide the absolute value of Wj here, and then use a homogeneous property for positive quantity by multiplying this to the right-hand side, raised to the power of m. Right. So there are some subtleties on how to handle negative weights by modifying this C into this C tilde, but it's effectively just a reparameterization of the neural network to make it the standard spline with linear combinations of the truncated power basis together with a mth order polynomial. Okay, so what's even more interesting is that the weight decay on 2-layer neural network and some versions of weight decay on neural network is equivalent to the so-called total variation regularization on the coefficients. It gives you this L1 regularization on the coefficients. So how it works is the following, right? So take this weight decay regularization. So notice that when m is equal to 1, when the ReLU activation is used, this is the standard weight decay, and the V and W, so they are the second and first layer weights. By the AMGME equality, we can obtain that this is equivalent to so we have this inequality. So it just turns out that by this reparameterization, the final solution, this is CJ, right? It's the same as a product of this quantity, right? So the idea is that since it only depends on the product, and we're optimizing over Vj and Wj, so this equal sign is always true in the optimal solution for solving this objective function, right? And for this reason, one can replace the objective function of weight decay training for neural network in this 2-layer case with the L1 norm of the coefficients on the truncated power basis, which is equal to the total variation of this function's m's derivative. Okay, so we didn't invent this technique, right? So this was folklore that has been known for many years, and I think it dates back to the 2004 paper by Buer and Monteiro on the equivalence of matrix Frobenius norm regularized matrix factorization and the nuclear norm minimization, which is a more general statement than this. Yeah, but what is nice is that having this equivalence, and together with Pachian-Nowak's characterization of representer theorem, so one can effectively say that whenever we choose a number of knots to be larger than, say, the number of data points n, then one can show that the solution, the functional solution to this optimization problem in terms of the function parameterized is equivalent to locally adaptive regression spline, which minimizes over all functions in the entire universe, right? And by Mammon and Van der Geer, these estimators on the right-hand side achieves the optimal rate for the total variation class. Okay, so that's a warm up, and we run some experiments on this and show that the equivalence between the two-layer neural network and locally adaptive regression spline and the efficient implementation, it's called L1 trained filtering, is actually also equivalent empirically. So for those who are coming from statistics, so these are like straightforward figures to see, but let me parse this for you. So I'm basically tweaking the regularization parameter lambda and the weight decay parameters for the different parameterization, either with ReLU network or the classical L1 trained filtering. And on the left, I'm showing the actual fitted functions. So with larger regularization, you see more regular functions. And on the right, I'm plotting the coefficients of the different basis functions and whether they're active or not. So as I trace the lambda or the weight decay parameter, it traces out the so-called regularization path, right? So we can see that for the smaller regularization, a lot of these knots are active, and on the right hand side, when the regularization is large, only a small number of knots are active. Okay, so what I want to point out is that these two figures, although there are some differences since we're using gradient-based training for weight-decayed ReLU networks, other than that, like they look almost identical to me, especially for the slightly larger weight decay and lambda region. Okay, so that seems to have like settled our question pretty satisfactorily, yes, because neural networks, they are able to achieve locally adaptive rate, and optimizing neural network achieves something that's almost equivalent to what a classical method is doing. But I argue that it's still pretty satisfactory because it doesn't actually tell us why neural network work better. And also, in order to achieve this, for the general M, for M larger than 1, right? So these are total variation classes with a higher order derivatives. It requires a non-typical activation function that use the truncated power basis as activation function rather than the standard ReLU. And the regularization term also needs to be modified from the standard weight decay. And in addition to that, it's not satisfactory because this method is not doing any representation learning at all, except where the knots are. And we know that without loss of generality, we can just put the knots as the observed data points instead of learning it. And that's not hurting us at all. And the fact that it deals with only a two-layer neural network and it doesn't say anything about deeper neural network just doesn't seem to be a satisfactory answer to the question that we posed at the beginning. Okay, so to address this problem, so we consider a slight modification to the deep ReLU neural network architecture by making it something called a parallel neural network. So what I'm showing is M, like slightly deep and a very skinny neural network called the subnetwork, right? So each one of these chunks is a subnetwork, so they have their own parameters, and the same data points is pushed into all of these subnetworks, and only in the end when the ensemble of this subnetwork is computed. Okay, so we train this jointly, and so this is like for people who know the jargon, this is called additive model. And you can also think about this as a standard wider like deep neural network with a weight matrix being constrained to have the kind of a block diagonal sparsity pattern, right? So it's either a parallel neural network or a standard neural network with a hard-coded sparsity pattern. And we're going to consider the objective function for training such neural network with weight decay regularization. Okay. So we didn't come up with this architecture. So the same kind of ideas of such a parallel subnetwork has been seen in SqueezeNet and ResNet from the empirical literature, and they has been theoretically studied in earlier work from a group in Stanford and a group in Johns Hopkins. Okay, so what we can show is that with the same idea of pushing through the scale of these weights all the way to the very end, we can reparameterize this L-layer neural network we can reparameterize this using something that resembles a linear regression objective function, right? So the idea is really to normalize the individual weights such that and push through the scale and combine all the scale as a single product at the very end, right? So this reparameterization allows us to write the objective function as something that looks like this. So notice that over here we have something called an LP norm of the coefficients that we use to take linear combination of this learned subnetworks. So a better figure to illustrate what I'm saying is that the loss function part of the neural network training can be reparameterized into something that looks like a linear regression, with a small difference being that the dictionary or the features are learned, and each column is a evaluation of the ReLU neural network on the n data points. And all we want to do is to learn this dictionary, but also learn a sparse coefficient vector and use a small number of these dictionary like atoms in this dictionary to linearly represent the labels that we observe. Okay, so it's really just linear regression, but with a learned representation. But what's nice is that we are not doing any explicit sparsity inducing regularization. We're just doing the standard rate decay. But it turns out that the standard rate decay in this function space is equivalent to this LP norm, where P, where this little p is equal to 2 over L. So as the depth of the network gets larger, then we're getting to more and more like stronger and stronger implicit sparsity inducing regularization on the coefficient vector. Okay. So that allows us to formally study this problem statistically and understand like whether the arc mean of the previous objective function is going to give us a locally adaptive rate, right? So we consider formally we consider the so-called boundary variation class of the mth order, which is the same as the total variation class that we talked about earlier, except that now this f needs to be in L infinity. And it turns out that it suffices for us to study the Besov class because the boundary variation class is sandwiched in between two Besov classes, and each of these two Besov classes has the same optimal rate for estimating function in between. So it suffices to study this bigger class, which would imply the optimal rate for the boundary variation class as well. And another thing to point out is that so far I only explained this thing in the univariate case when the input is one dimension. So that's also the case for the boundary variation class we're considering. But for the more general Besov class family, it can be higher dimensional as well. Okay, the performance metrics that we consider is the so-called mean square error defined on this empirical norm. So this is expectation is over the observed data, and x1 to xn is assumed to be fixed, and the error is only evaluated on the observed data points, but relative to the ground truth rather than the noisy observation. Okay, and then the observation model is that signal plus noise, and the noise is assumed to be independent sub-Gaussian. Right? So I hope the setting is clear. Okay, yeah, you don't have to understand what Besov class and total variation class is, but these are the natural family of function classes to study the problem of locally adaptive regression, local adaptivity in nonparametric regression paths, right? So what we showed is that parallel neural networks with an optimally tuned weight decay parameter indeed achieves a nearly optimal rate that's significantly better than the optimal rate that's achievable by linear methods, including all the kernel methods. So on the top, I'm showing that these are the rates that can be achievable by, say, neuron tangent kernels, and these are the rates that can be achieved by any method, right? The optimal method will have these rates. So let me parse the result for you. So for consider the Besov class under some mild restrictions on this alpha and Q. So what we can show is that there are two terms. So this term is like in some sense the generalization error bound, and this term is an approximation error bound. So the approximation error will go to 0 exponentially as the depth of the network gets bigger. So it suffices to choose the depth to be log n. On the left-hand side, right, also as L gets bigger, right, this rate will converge to the optimal rate of this minimax rate. Okay, so it suffices if we choose this L to be something like a C times log n, and the individual width of the subnetwork is also logarithmic also logarithmic in N.
Quick question.
Yes.
If you are interested in local adaptivity, why do you choose a globally defined metric for measuring performance?
Because because we're still trying to solve the nonparametric regression task, right? And we can, and the local adaptivity is localized because the function can have a varying degree of smoothness across different regions.
Mm-hmm.
Yeah, I think that's a good idea. So we could also think about like subintervals and consider the mean square error of individual subintervals, right? So that's not worked out, but I think that's highly doable, based on the tools that we've developed in this paper. Okay, so one thing that I wanted to point out is that the method doesn't know like what the function belongs to. The method doesn't know what this M should be, what this alpha, P and Q should be, yet it is automatically adapting to the most appropriate specification of the function classes to capture the ground truth that generates the underlying data. Okay. So several interesting insights. So first of all, there's a formal separation from kernels. So our upper bounds together with the linear smoother lower bound from Donahoe, Liu, McGibbon, like clearly separates the two family of methods, which says that neural tangent kernel is not really the right approach to understand the behavior of neural network, especially in these tasks. And then deep neural networks can do significantly better than kernels. Secondly, as we get deeper and our upper bounds achieve a smaller error than the shallow neural networks, it's not a formal separation of in terms of depths because we don't have lower bound, but clearly for shallow neural networks, so this approximation error is required since we only have ReLU, which represents the piecewise linear functions. If we hope the shallow neural network can be used to approximate, much smoother functions, and then it's really impossible. But we don't have a formal statement for that. And thirdly, so notice that like this neural network can be arbitrarily wide, right? We can have an arbitrary number of parameters. So as long as each individual subnetwork is sufficiently small, right? So overparameterization doesn't really cause overfitting, but the underlying mechanism why it doesn't cause overfitting is different from what's being studied in benign overfitting or in the NTK regime. So it is really due to the explicit regularization through the weight decay, which induces sparsity and which like we end up getting the generalization bound through the more traditional route. But the network itself can be overparameterized. So as long as you tune the weight decay parameter and to try to optimize it to the global optimal solution, and then things will be fine. Okay, so I think this slide might be revealing to people. So comparing to the classical nonparametric regression methods, so neural network, the parallel ReLU activated neural network can also be written in the same format. So all of these methods, splines and wavelets and neural network can be written as a linear combinations of certain basis functions. So the main difference is that different methods choose these basis functions differently and induce different sparsity pattern on the coefficients and slightly differently, right? So all of these methods are locally adaptive. So for train filtering and locally adaptive regression splines, the basis functions are hard-coded for each order of smoothness and with a NOS specified at the observed data points. And then they penalize L1 sparsity to select where the NOS are. Wavelet smoothing, on the other hand, you need to choose your favorite wavelets. So all the information are hard-coded in those chosen wavelets according to the level of smoothness of interest. And then depending on whether you use soft thresholding or hard thresholding for the wavelet smoothing, then it gives you different level of sparsity. So and all of them are rate optimal. For parallel deep neural network, so instead we use a parametric form for learning these basis functions G, right? So now each of these basis function is an individual subnetwork. And then the LP and the sparsity is even sparser than L1, but it's something in between L1 and L0, depending on the depth of the network. Okay, so I wanted to emphasize that it may appear to like intuitively. So now that we're doing a lot more, right? We are also learning these G's instead of hard coding this G, right? Statistically, that should cost us something. There should be a price to pay for doing more. Right, but interestingly, what we've shown that with the deeper neural network, learning the representation is not really hurting the statistical performance. So in some sense, we're paying almost nothing as the neural network gets deeper, and that's really surprising to me. And it might be like one of the reasons why like deep neural networks is such a remarkable tool. And all we have to do is to tune the weight decay and learning rate and to get it to work and use a standard cross-validation procedure. So that makes it more practical than some of these other methods. Okay, so let's look at some examples, some empirical examples. So on the left, I'm showing you the same Doppler-like functions with a ground truth in black and observations in dots. And different colors show the performance of different methods. So on the left, I'm showing the actual fitted value at a particular level of degree of freedom, effective degree of freedom. In the middle, I'm showing the mean square error. So this is how we measure the performance against the ground truth. And as we adjust the regularization parameters, they all are mapped to the effective degree of freedom so that they become comparable. So what we can see is that parallel neural network is doing a lot better with the optimal choice of hyperparameter comparing to the alternatives. Okay, what's more interesting is on the right-hand side, where I'm showing you the learned basis function from fitting a parallel neural network to this noisy data. So this network is like very like overparameterized. So there are many subnetworks, yet these are the only networks that are end up being active, right? So everybody else have a zero coefficient, and these are the only ones that are selected by the sparsity inducing regularization. So what this is saying is that weight decay is really inducing sparsity in the function space. And another thing is that the different basis functions seems to be representing the different frequency and representing different sub-regions of the underlying function, right? So this one like gives us some high frequency signal and then flat, almost flat everywhere else. And there are some other functions that can be used to reconstruct the different other regions, the smoother regions of the network, right? So intuitively, so that's how neural networks becomes locally adaptive. So let's make this even harder, and then consider this connections of piecewise linear functions and piecewise cubic function, right? So this is a regime that's not covered by the classical methods, because you have to specify whether you want a piecewise linear function or a piecewise linear fit or piecewise cubic fit if you use train filtering or locally adaptive regression spline, right? Same conclusion. So neural network with optimally tuned weight decay parameter is doing better than the classical locally adaptive methods, and the classical the best among these linear smoothers, right? It's not surprising that smoothing spline is not doing well in this case, because it's linear smoother. It has a suboptimal rate, but it is quite a surprise to us that the parallel neural network is actually able to do better than train filtering in this task. Okay. I started 5 minutes late, so I want to spend another 5 minutes just to explain like how some of this underlying stuff work. Is that okay for everybody?
Yeah, sure. I think those who may have other sessions might leave earlier, but I think, yeah, sure.
Okay, yeah, let's get to it. So the proof, the idea of the proof is to start from this proposition 14, where we analyze the mean square error by decomposing the error into the approximation error and the estimation error. Okay, and the estimation error is parameterized by this so-called metric entropy. So this is the log of the covering number of the function class. But there are some subtleties that we have to separate the function class into something that's parallel to and something perpendicular to a particular space, because the regularization has a null space, and we need to take care of that null space separately. Right, so there are some subtleties, and beyond that is a standard self-bounding argument for obtaining statistical convergence in statistical learning theory. Okay, and then we're gonna bound the approximation error and the generalization error separately, right? So another thing is that it might be surprising to you that this is 1/n, but what happens that how we get this fractional rate that reflects the optimal rate for this non-parametric family that goes into this metric entropy, right? So this term will depend on n. Right, so we end up getting the right n to the power of 3 over 4, minus 3 over 4. Okay, so approximation error bound is one of the more interesting part of this. So the idea is that so any Besov functions can be sparsely parameterized by a particular wavelets called the cardinal B-spline wavelets. So if we can show that the neural network, each subnetwork can approximate a particular little bump of this cardinal B-spline basis, upon translation and rescaling, we can use it to approximate the cardinal B-spline wavelets. Therefore, like showing that there exists a sparse representation for the underlying function in Besov family. Right, so we borrow some techniques which will allow us to show we can use the same neural network as long as it's slightly deeper and logarithmically wide. It can be used to approximate all these bump functions without knowing what the level of smoothness is. Okay, so let me illustrate like how this works and how the effect of depth is why depth is important in the approximation theory of neural networks. So again, we're doing just a ReLU activation. So the network can only represent piecewise linear functions. So this is how two-layer neural network with two weights can with just two neurons can best approximate a quadratic function, right? But as we make it deeper, and each layer only contains just two weights, right? So the number of parameters grows linearly, but we can get exponentially better approximation to this quadratic function. Once we can get a quadratic function, we can truncate and we can get higher order polynomials. So then we can use it to reconstruct the truncated power functions, and then further use it to reconstruct the little B-spline bumps, right? So that's the idea, right? So we only need the network to be slightly deeper for the approximation error to go to 0 exponentially. Okay, so the last step is to bound the metric entropy, and the idea is that all we have to work out is a metric entropy for the individual subnetworks, which is easy to calculate, and then we have this extension lemma proven, saying that for any like linear combinations of the functions within this subnetwork G, right, provided that this LP norm of this function is smaller than some constant, then we can bound the metric entropy using this, right? So this is really a more general extension lemma that says that we can do the sparse combination and then work out the metric entropy for the function class that represents an arbitrarily overparameterized but sparse represented neural network. Okay. Yeah, so that wraps it up. So let me summarize. So I talked about the separation from kernel methods. I talked about how deeper neural networks are better and why like neural network advantage can be explained from the angle of adaptivity. And ultimately, all we have to tune is a weight decay and no architecture search. And I illustrated that neural network is equivalent to sparse linear regression with representation learning, and the implicit sparsity is induced by the standard weight decay. And the nice thing about that is, as learned, the dictionary space is going to be very sparse, and in the test time, we can basically take what is learned and figure out what is active, and that gives us a very, very sparse and compact representation that can be used to deploy the network to, say, some edge devices. So L-Layer decay hypothesis, in some sense, like really, really valid over here. Right, so there are many things that we are just barely starting in this research thread. So there are many possibilities for future work and collaboration. So given that I'm out of time, so I won't go into any of this. And with that, I'll stop and thank you for your attention.
Thank you so much for your interesting talk. Particularly, these results are interesting for many people who are working on empirical research for deep learning. At the interest of time, I guess we don't have time for Q&A, but I'm sure if you have questions, you can reach out to Yu-Xiang directly for further discussion. Thank you, everyone. And I guess we can end this session.
All right, thank you.